Hey everyone, and welcome to today's Explainer. We're going to be going on a bit of a visual journey to unpack the really brilliant mechanics behind the number system. Instead of just looking at math as this rigid, boring set of abstract rules, we're going to explore how these concepts actually serve as a highly practical map of our everyday reality. We'll be covering the whole shebang: integers, absolute value, rational numbers, and inequalities. Okay, let's dive right into this.
So here is our roadmap for today. We're going to start with a welcome to the number system, then move into opposites on the number line, measure distance with absolute value, unpack rational numbers, and finally wrap things up with real-world inequalities.
All right, Section 1. Welcome to the number system, building from zero.
Now, it's incredibly helpful to think of math not as a rigid rule book, but honestly as a language designed to describe the real world. And our main character for today is the number line. This horizontal line stretching out forever in both directions. It isn't just a simple drawing, it's our entire mathematical landscape. It's the physical foundation for literally everything we're going to cover today. And right in the middle, that zero, well, that acts as our anchor. It's our ultimate starting point for measuring the world around us.
And that brings us to a really foundational definition: integers. So, an integer is the set of whole numbers and their opposites. What that means is it includes our familiar positive counting numbers, 1, 2, 3, starting with 0, but it also introduces this whole mirrored world of negative numbers. Actually, fun little side note here, negative numbers were largely considered completely absurd by early mathematicians. It wasn't until Indian scholars like Brahmagupta formalized them back in the 7th century to represent financial debts that they really took off. How crazy is that?
Moving on to Section 2, opposites on the number line, the mirror world.
Okay, so I want you to imagine that zero anchor as a giant mirror. The numbers on one side reflect perfectly onto the other side. Opposites are just values that are an equal distance away from zero, but on different sides. The absolutely crucial point to remember here is that they can be positive or negative, but what actually binds them as opposites is that perfectly identical distance back to that zero anchor.
This brilliantly illustrates how we actually use opposites in real life. Let's say you hop into an elevator and ride it up to the 9th floor. We represent that real-world upward action mathematically as a positive 9. But what about parking your car in a garage 4 floors underground? That descent below zero level is a negative 4. Positive and negative integers just work beautifully together to describe quantities moving in completely opposite directions.
Section 3, measuring distance, absolute value.
So what if we just don't care about the direction? Like, what if we just want to know how far we traveled? Well, absolute value is simply a number's distance from zero, interpreted as its magnitude. And because it measures pure distance, absolute value is always, and I mean always, positive. Just think about it. You can't exactly walk negative 5 steps, right? You just walk 5 steps. The magnitude is just the raw amount.
Let's apply this absolute value concept to reality. If the temperature outside suddenly drops to 15 degrees below zero, the integer is negative 15, sure. But the absolute value, the actual magnitude of that freezing chill, is just 15. Or say Michael has a $0 bank balance and overdrafts his account by $75. The integer is negative 75, but the absolute value, the true magnitude of his real-world debt, is simply 75.
Next up, Section 4, understanding rational numbers, the bigger picture.
Up until now, our number line has only really featured whole numbers, right? Just jumping cleanly from 0 to 1 to 2. But the real world doesn't always fit perfectly into whole numbers. We usually need to fill in the gaps. Think of the number system kind of like mathematical nesting dolls. Right in the center, we have our basic whole numbers, like 2. The next layer out adds integers, which brings in our negative numbers. And then the biggest, outermost layer represents rational numbers, encompassing fractions, like 1/3.
Formally speaking, a rational number is any number that can be written as a fraction, a over b, where both a and b are integers. And guys, this is the mathematical breakthrough that allows us to use decimals and fractions to pinpoint highly exact, incredibly specific locations anywhere in the empty space between our whole integers on the line.
Okay, let's actually put these rules to the test with a scenario directly from our source material. Our magic number today is negative 45. Keeping everything we just discussed about opposites, distance, and absolute value fresh in your mind, let's identify its properties.
Just take a really close look at negative 45 for a second. That negative sign dictates its specific direction from 0, while the 45 dictates its magnitude.
Those two very distinct pieces of information are totally key to understanding how it functions in our system.
Let's evaluate these statements analytically together. Statement 1. The opposite is 45. Yep, this is true. It's the exact same distance from 0, just sitting on the positive side. Okay, statement 2 claims negative 45 represents its absolute value. Well, actually, scratch that. This is decidedly false, because remember, absolute value is distance, and distance is always positive. The absolute value is just 45. And finally, is it 45 units away from 0? Yes, that is absolutely true.
And finally, Section 5, Inequalities in the Real World, Comparing Values.
So we know exactly how numbers populate our number line now. Integers on the major hash marks, rational numbers filling in the spaces between. But how do we accurately compare them to one another? Well, inequality statements do exactly this. They compare two values and describe their relative position. Fundamentally, they just tell us which value sits further to the left, meaning it's smaller, or further to the right, meaning it's larger.
Honestly, comparing values really just means translating everyday verbal phrases into strict mathematical order. If a word problem says something is less than or below, our mathematical translation just uses the less than symbol, pointing directly to the smaller value or lower position on our line. Saying negative 5 is below 0 is exactly the same as writing out negative 5, the less than sign, and a 0. It's literally just translating English directly into math.
We've covered some incredible ground today, from the mirror world of integers to the pinpoint precision of rational numbers. But as I mentioned at the very beginning of the explainer, this isn't just some abstract theory. This is the true language of your everyday reality. So I'm going to leave you with this question to end on. Look around you right now. What is one positive and one negative integer you can identify in your immediate environment? Is it a temperature on your thermostat, maybe a floor level in your apartment building, or a balance in a digital wallet? The number system is literally hiding in plain sight all around you, just waiting to be read. Thanks so much for joining me today.